So hi, I'm going to be looking at a textbook called Generating Functionology by Herbert Wolf. It's a freely available textbook. You can download it online from Herbert's website, I guess. It's quite famous, a little bit famous I've noticed. On the internet you get it mentioned a lot on some internet forums. People seem to like it, partially because it's free, and it's all about generating functions. So going to be looking at power series, where the coefficients form some interesting sequence. So we have some power series Fz something like this, an 10 to the n. An is some sequence, and this will be equal to some functions. So for example, if that was 1 over 1 minus z, all of the an are 1. Particularly interesting sequence, but I guess the idea for a book is to see what kind of sequences produce interesting functions, and see what sequences are produced by interesting functions, and using the functions and the ability to express a sequence in terms of a function like this to learn more about the sequence itself. I think that's part of the idea here. So so let's see what it says. We'll start at the so chapter 1, I guess. Chapter 1 is introductory ideas and examples. So I'll read it out. A generating function is a clothesline on which we hang up a sequence of numbers for display. What this means is this. Suppose we have a problem whose answer is a sequence of numbers, A0, A1, A2. We want to know what the sequence is. What kind of answer might we expect? A simple formula for an would be the best that one could hope for. If we find that an equals n squared plus 3 for each n, then there's no doubt that we have answered this question. But what if there isn't any simple formula for the members of the unknown sequence? After all, some sequences are complicated. To take just one hair-raising example, suppose the unknown sequence is 2, 3, 5, 7, 11, 13, 17, 19, etc., where an is the nth prime number. Well, then, it would be just plain unreasonable to expect any kind of simple formula. Generating functions add another string to your bow. Although giving a simple formula for the members of the sequence may be out of the question, we might be able to give a simple formula for the sum of a power series, whose coefficients are the sequence that we're looking for. For instance, suppose we want to know the Fibonacci numbers F0, F1, F2, and we know about and what we know about them is that they satisfy the recurrence relation. Fn plus 1 equals Fn plus Fn minus 1, and the sequence begins with 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. There are exact, not very complicated formulas for Fn, as we shall see later in example 2 of this chapter. But just to get across the idea of a generating function, here is how a generating functionologist might answer the question. The nth Fibonacci number, Fn, is the coefficient of x to the n in the expansion of the function x over 1 minus x squared as a power series about the origin. You may concede that this is a kind of answer, but it leaves a certain unsatisfied feeling. This isn't really an answer, you might say, because we don't have that explicit formula. Is it a good answer? In this book, we hope to convince you that answers like this one are often spectacularly good, in that they are themselves elegant. They allow you to do almost anything you'd like to do with your sequence, and generating functions can be simple and easy to handle, even in cases where exact formulas might be stupendously complicated. Here are some of the things that you'll often be able to do with generating function answers. A. Find an exact formula for the members of your sequence. Not always in a pleasant way, if your sequence is complicated, but at least you'll have a good shot at finding such a formula. B. Find a recurrence formula. Most often generating functions arise from recurrence formulas. Sometimes, however, from the generating function you will find a new recurrence formula, not the one you started with, that gives new insights into the nature of your sequence. C. Find averages and other statistical properties of your sequence. Generating functions can give stunningly quick derivations of various probabilistic aspects of the problem that is represented by your unknown sequence. D. Find asymptotic formulas for your sequence. Some of the deepest and most powerful applications of the theory lie here. Typically, one is dealing with a very difficult sequence, and instead of looking for an exact formula, which might be out of the question, we are looking for an approximate formula. While we would not expect, for example, to find an exact formula for the nth prime number, it is a beautiful fact, the prime number theorem, that the nth prime is approximately n log n when n is large, in a certain precise sense. In Chapter 5, we will discuss asymptotic problems. E. Prove unimodality and convexivity, etc. The sequence is called unimodal if it increases steadily at first and then decreases steadily. Many combinatorial sequences are unimodal, and a variety of methods are available for proving such theorems. Generating functions can help. There are methods by which the analytic properties of a generating function can be translated into conclusions about the rise and falls of the sequence of coefficients. When the method of generating functions works, it is often the simplest method known. F. Prove identities. Many identities are known in combinatorics and elsewhere in mathematics. The identities that we refer to are those in which a certain formula is asserted to be equal to another formula for stated values of a free variable or variables. For example, it is well known that the sum from j equals 0 to n of n choose j squared is equal to 2n choose n for all n. I didn't know that. So I'll test one out. So it's 2, 3. So 3 choose O plus 3, 1 to go all the way up to squares n there as well. Go all the way up to n plus 3, 2 plus 3, 3. That should be equal to 6 choose 3, which is equal to 6 times 5 times 4 over 3 factorial 6. So it's just equal to, should be equal to 20. Okay, so let's check. The other side is 20. 1 squared, 3 squared, 3 squared. So that's 18 plus 2. Yeah, it works. I wonder why. Pretty cool. Let's continue reading. One way to prove such identities is to consider the generating function whose coefficients are the sequence known. The generating function whose coefficients are the sequence shown on the left side of the claimed identity, and to consider the generating function formed from the sequence on the right side of the claimed identity, and to show that these are the same function. Cool. This may sound obvious, but it is quite remarkable how much simpler and much transparent many of the derivations become when seen from the point of view of the black belt generating functionologist. The snake oil method that we present in section 4.3 below explores some of these vistas. The method of rational functions in section 4.4 is new and does more and harder problems of this kind. G. Other. Is there something else you would like to know about your sequence? A generating function may offer hope. An example might be the discovery of congruence relations. Another possibility is that your generating function may bear a striking resemblance to some other known generating function, and that may lend you to the discovery of that your problem is closely related to another one which you never suspected before. It is noteworthy that in this way you may find out that the answer to your problem is simply related to the answer of another problem, without knowing formulas for the answers to either one of your problems. In the rest of this chapter, we are going to give a number of examples of problems that can be profitably thought about from the point of view of generating functions. We hope that after studying these examples, the reader will be at least partly convinced of the power of the method, as well as the beauty of the unified approach. Okay, so section 1.1. An easy two-term recurrence. A certain sequence of numbers A0, A1 satisfies the condition an plus 1 equals 2an plus 1. So I'll write this down. An plus 1 equals 2an plus 1, and a0 equals 0. So I'm just going to calculate first few terms. An plus 1 okay. There we are. So find the sequence. First, try computing a few members of the sequence. Well, I just did, to see what they look like. It begins with 0, 1, 3, 7, 15, 31. Yep, that's what I've got. These numbers look suspiciously like one less than the powers of 2. Yes, they do. So we could conjecture that an equals 2 to the n minus 1 for all n greater than or equal to 0, and prove it quickly by induction based on the recurrence. 1.1.1. But this is a book about generating functions, so let's forget all of that. Pretend we didn't spot the formula and use the generating function method. Hence, instead of finding the sequence an, let's find the generating function ax. So yeah, let's write this down. So let's work through their example with them. Ax equals n equals 0, a n x n. Okay. Once we know what the function is, we will be able to read off the explicit formula for the ans by expanding ax in a series. To find ax, multiply both sides of the recurrence relation 1.1.1 by x to the n and sum over the values of n for which the recurrence is valid, namely all n greater than or equal to 0. So let's try that then. So what we got recurrence was an plus 1 equals 2 an plus 1, so doing what they say, multiplying by both sides by x to the n equals 2an x to the n plus x to the n, and then they instruct us to sum over all n equals 0. Now I take the 2 outside, an x to the n plus n equals 0. Whoops. That's yeah, just x to the n. Yeah. And I'm going to jump ahead a little bit, and this thing here is geometric series, so I'm going to hop ahead a little bit, and I'll say this thing here is precisely ax, so I see where this is going, I think. Okay, so multiply both sides of the recurrence relation by x to the n and sum over the values for n for which the recurrence is valid, namely over n greater than or equal to 0. And then try to relate these sums to the unknown generating function ax. If we do this first to the left side, this results in the sum of n greater than or equal to 0, an plus 1 x to the n. Yep. So how can we relate this to ax? Well, it's almost the same as ax, but the subscript of the a in each term is 1 unit larger than the power of x. But clearly, so let's see. Let's work this out. So we've got we had an we had an plus 1 x to the n, and they've expanded it out like and then they've got they're compensating for the 0 here, so it's equal to yeah, so just writing in terms of so it's minus a0 and divided by x, and we know that a0 is equal to 0, so this is just ax over x. And so what we wrote before, I guess this is going to give us a way to calculate our ix. Since an equals 0, hence the result of operating on the left side of 1.1.1 is ax over x. Next, do the right side. Multiply it by x to the n and sum over all n greater than or equal to 0. Yeah, there was 2. Oops, missed that. Wherein we have used the familiar geometric series valuation. The sum of all x to the n greater than or equal to 0 is 1 over 1 minus x, which is valid for all x of absolute value less than 1. If we equate the results of operating on two sides, we find the following equation, which I have got written out here, which is trivial to solve for the unknown generating function ax. So let's just do that. So I'm going to take all of the ax over to one side. Ax 1 over x minus 2 equals 1 over 1 minus x. So ax equals 1 over 1 minus x, 1 over x minus 2, and I'm just going to multiply the top and the bottom by x, 1 minus x, 1 minus 2x. Is that what they've got? Yeah. So this is a generating function for the problem. The unknown numbers an are arranged neatly on this clothesline. An is the coefficient of x to the n in the series expansion of the above ax. Suppose we want to find an explicit formula for the ans. Then we would have to expand ax in a series. This isn't hard in this example, since the partial fraction expansion is so let's work out the partial fraction expansion. So we had ax is equal to x over, what was it, 1 minus x, 1 minus 2x. So this is going to be going to look like, I'm going to say ux plus vx over 1 minus 2x So let's equate the x constant coefficients, so minus x so this bit has to be 0 because there's no constant part on the left hand side, so and this bit has to be equal to minus 1, so ux 2ux plus vx equals minus 1, and we already know that vx is equal to minus ux, so 2ux equals ux equals minus 1. And so vx equals 1, and we have that ax is equal to 1 over 1 minus 2x minus 1 over 1 minus x, and using the geometric series expansion, n equals 0 to infinity 2x to the n minus n equals 0 x to the n because n equals 0 2 to the n minus 1 x to the n. So yes, there we see all of the coefficients are 2 to the n minus 1. just looking at this bit here, I guess for this to make sense, we need 2x, absolute value of 2x to be less than 1, or the absolute value of x to be less than a half. Okay. And they've done the same thing there, so they've their partial fraction expansion looks different than mine. You've got this 2 over 1 minus 2x minus 1 over 1 minus x. And they've taken the x out. Well, I guess that makes sense. And you've only got a constant on top to worry about. Maybe I should have done that. But I'm guessing it works out the same. Maybe. I hope. It looks like it should, right? Okay. So it's clear that the coefficient of x to the n, i.e. an, is equal to the n minus 1 for each n greater than or equal to 0. In this example, the heavy machinery wasn't needed because we knew the answer almost immediately by inspection. The impressive thing about generating functionology is that even though the problems can get a lot harder than this one, the method stays very much the same as it was here. So the heavy machinery may produce answers in cases where answers are not a bit obvious. Okay, I'm just going to quickly check that my function, that when I expanded it by into partial sums, was the same thing. So I had 1 over minus 2x minus 1 over 1 minus x is an a on the other hand. So let's just check that this is in fact the thing I'm after. So this is equal to 1 minus x minus 1 minus 2x over 1 minus x 1 minus 2x equals, in the top bit, 1's cancel, and we get a minus x minus 2x, so that's indeed the original function, 1 minus 2x, and there, that they have is x 2 over 1 minus 2x minus 1 over 1 minus x. I guess they're going to get a 1 on top, 2, 1 minus x minus 1 minus 2x. Yep. So you got 2 minus 1, so it's going to be a 1. You got minus 2x plus 2x, so that's just use a 1 on top. And yeah, it's the same thing. Alright. Alright, so now section 1.2, a slightly harder two-term recurrence. A certain sequence of numbers a0, a1 satisfies the conditions an plus 1 equals 2an plus n and a0 equals 1. So an plus 1 equals 2an plus n, a0 equals 1 this time. Okay, so just as before, I'm going to calculate the first few terms. So for a0 is 1, to a1 is n plus 1, so it's 2 times s plus so a0, 2a0 plus 0 would be 2, and then 2a1 plus 1, 5, 12, 24 plus 3, 27, 54 plus 4, 58, 58 times 2, 116 plus 5, 121. Okay. And yeah, looks like that's what they've got written down. So as before, we might calculate the first several members of the sequence to get 1, 2, 5, 12, 27, 58, 121. A general formula does not seem to be immediately in evidence. Does not seem to be immediately in evidence in this case. So we use the method of generating functions. That means that instead of looking for the sequence a0, a1, we will look for the function ax. So this time we've got ax just as before, from n greater than or equal to 0. What we have, so that ax is. Once we have found the function, the sequence will be identifiable as a sequence of power series coefficients of the function, asterisk. What's the asterisk? So it's a footnote. If you are feeling rusty in the power series department, see chapter 2, which contains a review of that subject. Okay. So, as in example 1, the first step is to make sure that the recurrence relation we are trying to solve comes equipped with a clear indication of the range of values of the subscript for which it is valid. In this case, the recurrence 1.2.1 is clearly labelled in the parenthetical comment as being valid for n greater than or equal to 2. Though surely, I mean, with these recurrence relations, you can extend them back into the negative direction, surely. So you'd have, then n was equal to minus 1, you'd have a 0 equals 2a minus 1 plus minus 1, and since we know a0 is 1, then maybe the n causes should be fine. So 2 equals 2a minus 1. Yeah, so a minus 1 equals 1. Yeah. No reason you can't continue that into the negative direction, because all you'd ever be doing, you'd just be using the formula a n minus 1 equals a n minus n over 2. No, that's not right. Minus n, you need a, so it was minus n minus 1. So see if that's right. So when n was 0, it should be 1 plus 1 over 2. So yeah, so no reason we can't continue that into the negative direction. So not sure why they're banging on about that here. Where were we? N equals 0, 1, 2. Don't settle for a recurrence that has an unqualified free variable. Okay. The next step is to define the generating function that you will look for. In this case, we are looking for a sequence a0, a1, a2. One natural choice would be the function ax equals sum of aj x to the j that we mentioned above. Okay. Next, take the recurrence relation, multiply both sides of it by x to the n, and sum over all the values of n for which a relation is valid, which in this case means sum from n equals 0 to infinity. Let's do that again then, just as we did before. So recurrence relation is an plus 1 equals 2an plus n, and yep, so two out again. So this one is a bit more interesting. So the rest is just like we had before. So this was 2ax, and this was ax minus a0. In this case, that was 1. We have this thing here. So I suspect that's what they're going to get to very quickly. Try to express the result of doing that in terms of the function ax that you have just defined. If we do that to the left hand side, the result is ax minus 1 over x. So yeah, same as what I've got there, because a0 is 1. So much for the left side. What happens if we multiply the right side of 1.2.1 by xn and sum over non-negative integers n? Evidently, the result is 2ax plus the sum n greater than 0 nx to the n. We need to identify the series the sum of nx to the n. Now I reckon a derivative is going to be involved here. Yeah. So there are two ways to proceed: A, look it up, or B, work it out. To work it out, we use the following stunt, which seems artificial if you haven't seen it before, but after using it 4,993 times, okay, it will seem quite routine. So, well, I'm just going to note the fact. So let's look at the geometric series, shall we? So we know the geometric series x to the n 1 over 1 minus x, and if we differentiate this with respect to x, the left hand side is easy. Which yeah, the left hand side is easy. And what's the right hand side? You get 1 minus x squared, and I think we need a minus 1 up here. Think about that for a second. Differentiate we differentiate 1 over x, you get minus 1 over x squared, and then we'd need to so it's just going to be 1. Here I'm just using the fact that if you take the derivative, is it a chain rule? Yeah, the chain rule. And I know that the derivative of 1 over x is x to the minus 1 minus x to the minus 2. So I'm just doing this where f was the function 1 over x, and g is the function 1 minus x. G is a function 1 minus x, so you would have derivative of g was a minus 1, and f itself was minus 1 over x squared, but we put the g exercises again, another minus 1 over 1 minus x squared, so that's how I got 1 over 1 minus x squared. So this thing here is 1 over x of the thing we wanted, so if we multiply it all through by x, put an x up there, we have that this is equal to ooh, what have I done? I've written nonsense. What I meant to write was the thing we're after is equal to x over 1 minus x squared. So our equation for ax becomes, what is it, 2ax plus, so hopefully I've not done anything too silly, and this should be the same as what I come up with. So they're saying that this thing is equal to, so that they're just saying that nx to the n is equal to x times d by dx x to the n, and then so they've done this, and then they've taken the derivative outside the infinite sum, so there's the sum both sides here, then they've taken the derivative out. And this gives them which is the same thing that we calculated. I guess you need to be careful, don't you, taking derivatives outside an infinite sum, but whatever. We get the same thing, yeah. X over 1 minus x squared, so phew. In other words, the series that we are interested in is essentially the derivative of the geometric series. So its sum is essentially a derivative of the sum of the geometric series. Sorry. In other words, the series that we are interested in is essentially the derivative of the geometric series. So its sum is essentially the derivative of the sum of the geometric series. Are they trying to explain how that they took the dx outside there? That doesn't mean too much to me. When they say derivative of geometric series, are they... whatever. I think they're trying to explain how they've taken the dx to the outside of the sum. This raises some nettlesome questions which we will mention here and deal with later. For what values of x is 1.2.2 valid? The geometric series converges only for x of absolute value less than 1. So The analytic manipulation of functions in 1.2.2 is legal only for those x. However, often the analytic nature of the generating function doesn't interest us. We love it only for its role as a clothesline on which our sequence is hanging out to dry. In such cases, we can think of a generating function as only a formal power series, i.e. as an algebraic object rather than as an analytic one. Then 1.2.2 would be valid as an identity in the ring of formal power series, which we will discuss later, and the variable x wouldn't need to be qualified at all. Anyway, the result of multiplying the right hand side of 1.2.1 by x to the n and summing over all n greater than 0 is 2ax plus x over 1 minus x all squared. Yeah. And if we equate this with our earlier result from the left hand side, we find that, and they've got the same equation that we came up with earlier. So, and we're ready for the easy part, which is to solve 1.2.3 for the unknown ax. So let's do that. This was 1.2.3, this thing here. So that was meant to be an x, wasn't it? Sorry, getting over a cold. Let's put the ax over to the left, see if we can do this without making any mistakes. So we have 1 over x minus 2. On the right hand side, we have to take this 1 over x over, I don't want to forget that part, plus x over 1 minus x squared. Okay, and divide through. This is minus 2, and I'll tidy this up a bit. So first I'm going to multiply top and bottom through by x 1 minus 2x popping up again, and then I'm going to multiply top and bottom by 1 minus x squared to get rid of this quotient here. So 1 minus x squared plus x squared over 1 minus 2x 1 minus x squared, and expand out the top part. It's going to be 2x squared plus minus 2x plus 1 all over 1 minus 2x 1 minus x squared. Okay. Yeah, wow, I've got the same as them. Brilliant. So exactly what have we learnt? The original problem was to find the numbers an that are determined by the recurrence 1.2.1. We have, in a certain sense, found them. The number an is the coefficient of x to the n in the power series expansion of the function 1.2.4, which is what we found, the function that we just calculated. This is the end of the find the generating function part of the method. We have it. So what we do with it depends on exactly why we wanted to know the solution of 1.2.1 in the first place. Suppose, for example, that we want an exact simple formula for the members of an of the unknown sequence. Then the method of partial fractions will work here just as it did in the first example, but its application is a little bit trickier. Let's try it and see. Well, I struggled a bit with my continued fractions in the last section, but I'm gonna give this a go. See if I can do this without too many problems. So this time I'm going to take all of just leave a constant on the top. We had, what was it, 1 minus 2x, and it was 1 minus x squared. Well, I'm going to start off using what we had last time. Which I'm pretty rusty with partial fractions, you might have noticed. So well, last time we had that 1 over 1 minus 2x 1 minus x was equal to 2 over 1 minus 2x minus 1 over 1 minus x. So this thing here, we just need to multiply it through by another. So this thing is 1 over 1 minus x times 2 over 1 minus 2x minus 1 over 1 minus x. Expanding this out, we have 2 over 1 minus 2x 1 minus x minus 1 over 1 minus x 1 minus x squared. And this was a 2, wasn't it? Looks like I've written a z. 2. And we know what this bit is again. So this is, because this is just twice this. So this is 4 over 1 minus 2x minus 1 over, minus 2 over 1 minus x minus 1 over 1 minus x squared. So let's see if that's, I'm just going to look ahead, if that's what they've got. Okay. They've done it completely differently. They just jumped straight in, I think. They didn't take out the polynomial on top of the fraction this time. The first step is to expand the right side of 1.2.4 into partial fractions. Such a fraction is guaranteed to be expandable in partial fractions in the form that they've written, that 1 minus 2x plus 2x squared over the 1 minus x squared 1 minus 2x is guaranteed to be expressible in the form I'm a bit curious because I'm guessing they mean a, b and c are constants, and we have a square term up here. So I don't remember much about partial fractions, but if we had a really big power up here, you know, x to the 10, would you still be able to write this in this form of a, b and c constants? Probably. Maybe not. Probably not. Maybe the fact that this is only a square means that we can. I don't know. So let's see what happens the way they solve it. So here's the quick way. First, multiply both sides of 1.2.5 by 1 minus x squared. So they get 1 minus 2x plus 2x squared over 1 minus 2x plus, equals a plus 1 minus x b plus 1 minus x 1 minus x squared c over 1 minus 2x. And then they say let x be equal to 1, which so this is going to hold for all x. It better I'll hold for x equal to 1. So this becomes 1 minus 2 plus 2 over 1 minus 2. So it becomes minus 1 equals a, plus b disappears. And the c disappears, and this term disappears. So yeah, so a is minus 1. The next is to multiply 1.2.5 by 1.2x and let x equal a half. Okay. So we have, going to get, so 1 minus 2x plus 2x squared, so they're multiplying it by 1 minus 2x, 1 minus x squared equals a over 1 minus x squared plus b over 1 minus x. We knew that this was minus 1. Plus c. Now we're letting x equal to, we're meant to be multiplying through by, so I've missed out 1 minus 2x here, 1 minus 2x. Letting x equal to a half obviously kills these terms. What to do up here? So we're going to have 1 minus 2 halves, which is 1, plus, so it's going to be 2 times a half squared over 1 minus a half squared, and this is going to be equal to c. And this is a half. C equals a half over a quarter, which is 2. So that gives us, let's see if that's what they say. If they say c equals 2, so the hard one is to find b. Well, let's do that one by cheating, they say. Since we know that 1.2.5 is an identity, i.e. true for all values of x, let's choose an easy value of x, say x equals 0, and substitute that value of x in. So into the whole equation, so it's going to become 1 minus 0, so it's going to become 1 over 1, which is going to be equal to a over 1 plus b plus c. And we know what a, b, a and c are, so that's minus 1 and c is 2. Oh, that's clever, I like it like this. Don't weigh you as much. B equals 0. Oh, that's nice. That's so nice. They've got such a simple solution. I think they knew in advance they were going to get a nice and easy partial fraction. So yeah, I'm glad I went through that. That was cool. Cool trick. See if we can remember that next time. Maybe I want to see how to do that sort of thing. I don't know. Yeah, so we have this lovely simple expansion here. What we are trying to do is to find an explicit formula for the coefficient of x to the n in the left side of 1.2.6. Well, I reckon I can get that pretty easily. So if we remember correctly, I can get it pretty easily from this, I think. So if I remember correctly, the 1 over 1 minus x squared is equal to derivative of 1 over 1 minus x. So this bit here is going to be equal to n equals 0, n x to the n minus 1. Which we might as well sum from n equals 1, because when n equals 0 this term's 0. And then I'm going to reorder it to go from n equals 1, this is, yeah, so I'm going to reorder that to go from n equals 0, n plus 1, x to the n. And this bit up here, okay, I missed off my minus. 1 over 2x, we just do the, so it's equal to 2, it's geometric expansion, n equals 0, and that would be 2 to the n, x to the n. So combining these, I suspect that we will get n equals 0, 2 to the n plus 1 minus n minus 1 x n. So is this the formula? Is this the correct formula for an? So a n equals 2n plus 1 minus n minus 1. Does that work for the first few terms? So is n equals 0 should be, so a0 should be 2 to the 1 minus 0 minus 1 equals 2 minus 1 equals 1. That's right. Let's try a bigger one. So we calculated them up to 6. So let's try a6. a6 equals 2, 7, 128. 8 powers of 2 minus 6 minus 1, 121. Well, that looks very close. That's exactly what we had, if I remember rightly. So yeah, I suspect that that is the solution. And that's what they've got written here. Woo! So let's continue reading. Where were we? What we are trying to do is find an explicit formula for the coefficient of x to the n in the left side of 1.2.6. We are trading that in for two easier problems, namely finding the coefficient of x to the n in each of the summands on the right hand side of 1.2.6. Why are they easier? The first term, 2 over 1 minus 2x, for instance, expands as a geometric series. The coefficient of x to the n here is just 2 to the n plus 1. The series, minus 1 over 1 minus x all squared, was handled in 1.2.2 above, and its coefficient is minus n plus 1. Minus n minus 1. If we combine these results, we see that our unknown sequence is an equals 2 to the n plus 1 minus n minus 1. Woo! Having done all of that work, it's time to confess that there are better ways to deal with recurrences of the type 1.2.1 without using generating functions. What's the footnote? See, for instance, chapter 1 of my book. Different book. Algorithms and Complexity. Wilf Herbert S. 1986. However, the problem remains a good example of how generating functions can be used, and it underlines the fact that a single unified method can replace a lot of individual special techniques in problems about sequences. Anyway, it won't be long before we're into some problems that essentially cannot be handled without generating functions. End of proof. It's time to introduce some notation that will save a lot of words in the sequel. So, definition. Let fx be a series of powers of x, then by the symbol square brackets x to the n fx, we will mean the coefficient of x to the n in the series fx. Here are some examples of the use of this notation. So xn e to the x equals 1 over n factorial, because the well-known expansion e to the x equals n equals 0 to infinity x to the n, where by convention or factorial is 1. Another example is 1 over 1 minus 3t. The t to the r square brackets 1 over 1 minus 3t. It's 3 to the r, yeah, because this is just a geometric series. Ratio of 3t. And then they have the nth coefficient of 1 plus u to the s. So s is fixed constant, the nth coefficient is s, choose m. So obviously, what's it called? The binomial formula. I equals 0 to s. S choose I. UI, pretty sure that's right. And again, by convention, if I greater than s, si equals 0, so we can just write this as an infinite sum if we like. N choose should have been an s. No, it's s choose n. S choose n, u to the n. Write it like that. Right, a perfectly obvious property of this symbol that we will use repeatedly is the coefficient of x to the n of x to the a fx is the coefficient of x to the n minus a of fx. Cool, yeah. I guess it's useful having that notation when you're proving things like that. It saves you writing annoying little sentences explaining what's going on. Another property of this symbol is the convention that if beta is any real number, then what do they mean when they're saying the beta coefficient bx to the n? What was their definition precisely? I mean, the coefficient of x to the n in the series fx, and they've got this minus beta x to the n. What's beta going to be? Is the beta a constant? It's a real number? So what on earth do they mean? Maybe it's equal to 1 over beta. They're saying it's just a convention. Okay, so it's just a convention, and yeah, so I guess it's saying what is the coefficient of beta x to the n, by which they mean if f equals this, if it's got this expansion, then the nth term is an x to the n equals an over beta times beta x to the n. I guess that's what the conventions for. And so this bit here is equal to 1 over beta of, yeah, that's all I mean, I guess, by that. So for instance, square brackets xn over n factorial e to the x is 1 for all n greater than or equal to 0. Before we move on to the next example, here is a summary of a method of generating functions as we have used it so far. So the method. Given a recurrence formula that is to be solved by the method of generating functions, 1. Make sure that the set of values of a free variable, say n, for which the given recurrence relation is true, is clearly delineated. Though I'm not sure why that's important. I guess you run into the problem of your I guess in general you might have recurrence relations that don't extend backwards, and the theory of power series becomes a different theory if you extend your powers of x to negative direction, especially if you allow arbitrary large, well, so it's like power series in both directions sort of thing. It might become a bit different, a bit of a different theory, I don't know. 2. Give a name to the generating function that you will look for, and write out that function in terms of the unknown sequence. E.g., call it ax and define it to be the sum of anx to the n. 3. Multiply both sides of a recurrence by x to the n, and sum over all values of n for which a recurrence holds. 4. Express both sides of the resulting equation explicitly in terms of your generating function ax. 5. Solve a resulting equation for the unknown generating function ax. 6. If you want an exact formula for the sequence that is defined by the given recurrence relation, then attempt to get such a formula by expanding ax into power series by any method you can think of. In particular, if ax is a rational function, quotient of two polynomials, then success will result from expanding in partial fractions and then handling each of the resulting terms separately. Okay, so it's the end of section 1.2. I think I'm going to stop there because that's gone on quite a long time. Section 1.3, let's just have a quick look ahead. We appear to look at Fibonacci numbers. And more stuff. Section 1.4, a three-term boundary value problem. Section 1.4 looks pretty long. Section 1.5, two independent variables. So yes, interesting. It's like the formula for n choose n, isn't it? It's the recurrence relation that's involved there. 1.6. So this chapter goes on a long way. Yeah. And then finally exercises. So, well, I think at least with chapter 1 I'm going to work all the way through it, and I'll probably even go at the exercises, see how those work out. Yeah, it's been quite cool so far. So, there we go.